Hi, welcome to Physics 2211 Lab 3 Black Hole. My name is Maria Jyotish and let's get started. In Part 1, the purpose of this lab is to find the mass of the black hole by analyzing the star's net force along its orbit, and in Part 2 to find the initial velocity at which a rocket launched off a planet would fly around the black hole as close as possible without crashing or being sucked in given the black hole mass calculated in Part 1. Some fundamental physics principles and models we can see in this lab are Newton's second law, the momentum principle, which relates the net interaction between the system and its surrounding to the observed motion. We will also see Newton's universal law of gravitation, which describes how two bodies exert gravitational forces on each other, where the direction of the force on either body is toward the center of the mass of the other body. And for a brief preview, in Part 1 we get that the mass of the black hole is 1.13 times 10 to the 34th kilograms, and in Part 2 the closest approximate initial velocity is negative 7.1 times 10 to the 7th meters per second in the x component and 2 times 10 to the 6th meters per second in the y component. As stated earlier, the purpose of Part 1 is to figure out the black hole's mass using its net force along the path it takes. We apply the momentum principle here because it describes how a system's change in motion when it experiences a net force, which will lay out our path. So as you can see, the net force is equal to the change in momentum over time. And in our situation, the net force is also equal to its parallel plus perpendicular component. We know that the parallel component is the motion of the object, which is equal to the change in magnitude of momentum divided by the change in time multiplied by p hat. And the perpendicular component is the change in direction, which is perpendicular to the parallel component. Later, we will also be applying the position and velocity update formulas. The universal law of gravitation uses the formula here to describe the force of attraction between two bodies. A key point to note here is that since this is in space, the only forces acting on the star is the gravity of the black hole, and the only forces acting on the spaceship are gravity from the black hole and from the planet. Hence, we will be setting the net force equal to the gravitational force. Because universal gravitation is non-constant, we will approximate the average force with the final velocity. Next, I use GlowScript to create a computational model of the star orbiting the black hole, the system being the black hole and the surroundings being the rest of the universe. The initial conditions are the mass of the star, the time of first observation, which is 0, the change in time, which would be a day and is displayed in seconds, and the gravitational constant. Now down here, we calculate the net force using the momentum principle. Then we find the individual parallel and perpendicular components of the net force. Last, we calculate the mass of the black hole by using the universal law of gravitation. Using Excel to calculate the average mass of the black hole, I got 1.13 times 10 to the 34th kilograms to be the mass. For Part 2, I created a computational model that displayed the spaceship going as close as possible to the black hole, the system being the spaceship and the surroundings being everything else. The initial conditions were the black hole mass, which we calculated in Part 1, the planet's speed and velocity, which we approximate ourselves later. To calculate the net force, we first find the net force of the black hole on the planet, and then the force of the ship on the planet, and then adding these together we get the net force on the planet, which we use to find r and r hat. Then we use the universal law of gravitation. Next, we use the position and velocity update formula to move the planet and spaceship. For our results, you can see that we got 7.1 times 10 to the 7th meters per second in the x component and 2 times 10 to the 6th meters per second in the y component. Some errors that may be present in this lab are not properly calculating the mass of the black hole, which would impact the entirety of Part 2, or not finding the closest initial velocity by which the spaceship would fly closest to the black hole. Follow-up questions ask, what is the difference between the net force and its parallel and perpendicular components, and the rate of change in momentum and its parallel and perpendicular components? There is no difference between the parallel and perpendicular components. It's just easier to find the change in momentum than it is to find the net force. Next, for the what-if question, I guessed and checked and found out that in order to orbit, the ship should have a similar velocity to the planet, but the y component must be slightly larger and the x component should be smaller and negative in order to avoid collision. This resulted in my initial velocity of the ship being negative 6 times 10 to the 7th in the x component and 3 times 10 to the 6th in the y component, meters per second. Thank you for watching.